Good morning students. Today is lecture 25 under module 9 and under this module basically we will be discussing in today's lecture as well as in subsequent lecture I will solve some of the numericals. So, today's lecture we will solve some numericals based on reverse osmosis and microfiltration. So, let us see the problem 1. It has been given something like this, calculate the water and salt flux of a cellulose acetate membrane used to desalinate a 5% sodium chloride solution at an operating pressure difference of 100 bar with a salt rejection of nearly 100%. The flux of pure water through the membrane is 100 liters per meter square hour at a pressure difference of 100 bar. The osmotic pressure of 2% sodium chloride is given as 11.5 bar and the polarization module M is can be taken as an unity. Now, in the second one in the same problem, it is being asked that the same module is used to desalinate a 4% solution of another salt at a osmotic pressure of 20 bar and polarization module M is given as 3 with a salt rejection of 0.99. So, what is the water and salt flux at an applied pressure difference of 75 bar? Also calculate the mass transfer coefficient. Now, note that the salt rejection can be assumed to be independent of pressure. Now, let us try to solve this problem. So, it is a good practice that whenever a problem is been given, so you please note down what is the initially when you try to solve it, please note down what are the data is given and the equations that you require. So, it has been given that pure water flux, that is we can write as JW, it is given as 100 liter per meter square hour. So, we can write as 0.1 meter cube per meter square hour. Then pressure difference is given, that is delta pi. So, delta pi is given as 100 bar. So, your pure water flux, or I will write just JW. So, JW equals to LP into delta pi. LP is the permeability, you know that from our earlier discussions and equations. So, we can find LP from this equation. LP equals to JW by delta P. So, JW is given 0.1 and delta P is 100. So, it is 10 to the power of minus 3 meter cube per meter square hour and bar. So, this is your permeability LP. Now, we have to calculate the water flux for a 5% NaCl solution as well as salt flux, right. So, it is given that the polarization module we can write, that is M, capital M is nothing but Cm by Cb. It is given as 1 in this particular case, and it is also given that the salt rejection coefficient R equals to 1. So, this indicates when the salt rejection is unity. So, this indicates Cp equals to 0. So, that means the salt concentration in the permeate side equals to 0. So, now we can calculate the osmotic pressure difference, the delta pi between the feed and permeate. So, you have to calculate the delta pi between the feed and the permeate. So, delta pi equals to pi of 5% NaCl, right. So, it is given that the osmotic pressure of a 2% sodium chloride solution is 11.5 bar. So, it is given pi of 2% NaCl is 11.5 bar. Now, we can calculate pi of 5% NaCl from that data of 2% NaCl. So, basically you see that it is 11.5 into 5 divided by 2, which is 28.75 bar. You know, this is taken from this equation, pi equals to CRT. Now, water flux JW for 5% NaCl okay, equals to LP into delta P minus pi. Okay. So, that is 10 power of minus 3 LP, just we have calculated LP 10 power of minus 3 into delta P is equal to 100 minus pi is 28.75. So, you get 0.07125, the unit will be meter cube per meter square hour. Okay. So, this is the water flux for 5% of sodium chloride solution. Now, you know that salt flux Js of 5% NaCl equals to 0, because your salt rejection, okay, is 1, right, R is been given 1. Now, we will try to solve the second one. Okay. So, which is called the same module, right. The same module is being used, it is been told that the same module is used to desalinate a 4% NaCl solution, okay, at a osmotic pressure of 20 bar, and polarization module is also given as 3, and the salt rejection R is given 0.99. Now, you have to calculate what is the water and salt flux, okay, at an applied pressure difference of 75 bar, and then we have to calculate the mass transfer. So, let us see the water and salt flux at 5% NaCl solution, right. So, here concentration polarization M is given as Cm by Cb, which is given as 3, right. So, you can calculate Cm here, Cm equals to 3 into Cb. So, 3 into Cb is given as 4%, so sodium chloride. So, here Cm is 12%. Now, salt rejection R is given as 0.99. Okay. So, we have to calculate Cp. So, Cp is the concentration of the salt in the permeate side. So, that is 0.01 into 12 is 0.12%. Do you get it? So, 99% of salt rejection means that the only 0.01% of salt is going inside the permeate side. So, Cp equals to 0.01 into 12, 12 is the concentration of the salt, right. Now, pi equals to 20 bar at 4%, okay, of NaCl, it is given in the problem statement. Okay. So, what is this? So, this is the osmotic pressure difference between the feed and the permeate. So, now we have to calculate delta pi. So, delta pi equals to Cm minus Cp into here into 20 divided by 4. Okay. So, which is 12 minus 0.12 into 20 divided by 4, or your delta pi becomes 59.4 bar, right. Then we have to calculate the water flux. Okay. So, this is your osmotic pressure difference between the feed and the permeate for this particular case of 4% sodium chloride solution. So, now we have to calculate water flux. So, your water flux Jw at 4% NaCl, okay, is Lp into delta P minus pi, right. So, Lp is that 10 power of minus 3 into delta P is 75, and this is we have calculated as 59.4. So, Jw here Jw, okay, it comes to be 0.0156 meter cube per meter square hour. So, this is your water flux that we have calculated for a 4% sodium chloride solution with the same module that is being used. So, then we have to calculate the salt flux at 4% NaCl. Okay. So, is nothing but Jw into Cm into 1 minus R. Okay. So, Jw we know 0.0156 we have just calculated into Cm equals to 120 into 1 minus R is 0.99. So, we will get 0.0187 kg per meter square hour. So, this is your salt flux for a 4% sodium chloride solution. Now, next we have been asked to calculate the mass transfer coefficient. So, to calculate the feed side mass transfer coefficient, you can use the equation Cm minus Cp divided by Cb minus Cp equals to exponential to the power of Zw by Kl. So, this Kl is your mass transfer coefficient, right. So, now you please substitute all the values and then you will calculate what is this is. So, basically it is Cm is 12 minus 0.12 divided by Cb is 4 minus again 0.12, right. So, equals to exponential to the power of Zw is by Kl. So, we will find out Zw by Kl equals to 119. So, we know what is Zw. So, from here we can calculate what is Kl. So, Kl the mass transfer coefficient is 0.0156 divided by 1.119, which is 0.0139 meter per hour, or we can write it 3.87 into 10 power of minus 6 meter per second. Usually mass transfer coefficient is being expressed as meter per second. So, you get your mass transfer coefficient on the feed side to be 3.87 into 10 power of minus 6 meter per second. Now, this is how actually you use to calculate the salt flux as well as water flux. So, you can see that in the first one we have to calculate salt and salt flux and water flux. It's the rejection is 100%. So, the salt flux is equals to 0. So, everything is getting retained on the surface of the membrane. So, no, the permeate does not contain any salt. So, it is R equals to 100. Now, in the next case R is given as 0.99. So, that means the only 0.01% of the salt is going to the permeate side. So, with that we have calculated the salt this one water flux as well as the salt flux, and again then we have calculated mass transfer coefficient using this particular equation. So, this is one classic example that how you can calculate water flux and salt flux, provided you know the concentration, polarization modulus and some other data like pressure difference. Of course, you can calculate osmotic pressure if osmotic pressure data of a salt solution is given in a particular value, then you can extrapolate, interpolate and calculate it. Okay. So, next another problem, let us see another reverse osmosis problem. So, here the problem says that in a cellulose acetate RO membrane of 12 micron thickness, the water flux is 5.2 microgram per centimeter square second and the salt flux is 0.015 microgram per centimeter square second at 25 degrees centigrade. So, on the feed side of the membrane, a 4% sodium chloride solution is used and the permeate side salt concentration is kept at 0 by continuous flushing with distilled water. The transmembrane pressure difference is 90 atmosphere and the osmotic pressure of 4% sodium chloride solution is 38 atmosphere. Now, the water solution can be taken as 0.15 gram per centimeter cube. Calculate the water diffusivity in the membrane. So, it is given that if you have to calculate the water diffusivity, this is what is being asked. So, some data is given that if the equilibrium solution of sodium chloride follow the Henry's law, then the Cs is given by this equation Hs into Cf, where Cs is gram of sodium chloride per centimeter cube of membrane volume and Cf is gram of sodium chloride per centimeter cube of feed. So, Hs Henry's constant is given as 0.037. So, you calculate the salt diffusivity. So, you have to calculate the water diffusivity as well as salt diffusivity. So, let us see how you will do it. So, this is a classic example from the solution diffusion model. You have to use the solution diffusion model to solve this problem. Okay. So, the solution diffusion model. So, you know This model is very important in membrane this one calculations, especially when we are talking about. So, I just rewrite this equation dW Cw V 1 divided by R T small lm into delta P minus delta pi, right. So, you have to calculate the diffusivity. dW is their water diffusivity, okay. Jw is the water flux, V is the volume of the this one molar volume of water, RT has its all meaning, temperature, T is temperature, Lm is the membrane thickness, delta P is the pressure that is applied, delta pi is the osmotic pressure. Now, it is given, then the salt concentration on the permeate side, okay, on permeate side, that is given as 0. Okay. So, which indicates that the osmotic pressure, okay, osmotic pressure that pi equals to also 0 in the permeate side. Now you can calculate the osmotic pressure difference. So, delta pi equals to, it is 38 minus 0, okay. So, is nothing but 38 atmosphere, because the osmotic pressure at the permeate side equals to 0. So, the overall osmotic pressure difference is 38 atmosphere. So, its delta P is the transmembrane pressure, it is given 90 atmosphere. So, effective pressure difference, or we can say driving force, is nothing but delta P minus delta pi. So, it is 90 minus 38 equals to 52 atmosphere. So, 52 is the effective pressure driving force. So, other data that is given, it is given Cw equals to 0.15 gram per centimeter cube, or we can write in terms of kg is 150 kg per centimeter cube, right. So, Jw, which is your water flux, okay, is 5.2, this is micrograms, okay, per centimeter square second. So, you can write it as 5.2 into 10 power of minus 5 kg per meter square second, and membrane thickness Lm is given as 12 micron. Okay. So, 12 into 10 power of minus 6 meter, just converting everything in terms of meters and kilograms. So, that there will be unit consistency, and temperature T is given as 25 degree centigrade equals to 298 Kelvin. Okay. So, for a dilute solution, you have to see the V. Okay. So, molar volume of water V 1 equals to 18 centimeter cube per gram mole. Okay. So, we can write 0.018 okay, meter cube per kilomoles, and your gas constant R equals to given 0.0821 meter cube atmosphere divided by Kelvin kilomole. Okay. Then we have to calculate now, substitute everything in this equation, the solution diffusion equation. So, Jw equals to again I am just writing dW Cw V 1 divided by R T, Lm is the membrane thickness, then delta P minus delta pi. So, just substitute 5.2 into 10 power of minus 5 equals to dW, that is what we do not know, we are calculating, okay, into 150 into 0.018 then divided by 0.0821 into 298 into Lm is 12 into 10 power of minus 6. We have converted everything into meters, okay, into 52 is delta P minus delta pi, the true driving force. So, from here we will calculate dW, the water diffusivity equals to 0.087 into 10 power of minus 10 meter square per second. So, this is your water diffusivity. Now, we have to calculate the salt diffusivity, which is ds. You know, salt flux is given as, okay, salt flux, that is Js. Js equals to minus ds, the salt diffusivity, into delta Cs divided by Lm. Lm is the membrane thickness, right. So, Js is given as 0.015 microgram per centimeter square second, okay, or we can write 1.5 into 10 power of minus 7 kg per meter square second, correct. If you neglect the concentration polarization, then the feed side salt concentration can be given as, so you can write that neglecting concentration polarization. So, we can calculate the feed side salt concentration, that is CS1, okay, is equals to HS into CF. So, this is from Henry's law, okay. This is also given, problem statement is given, okay. So, HS is given, so HS is given as 0.037, okay, and CF equals to gram NaCl, okay, per centimeter cube feed, okay, that is CF is also given. So, here CS1 CS1 it is CS1, okay, equals to 0.037, that is HS into 4 by 100, okay. So, it is 1.48 kg per meter cube. So, then this is feed side. Similarly, you have to calculate the permeate side, that is CS2. So, CS2 equals to 0, okay, because there is no diffusivity, then here Lm membrane thickness is given is 12 into 10 power of minus 6 meter. So, you can calculate Js by substituting in that equation. So, Js equals to minus ds delta Cs by Lm. So, here we can calculate ds from here, ds salt diffusivity equals to 1.5 10 power of minus 7, okay, into 12 into 10 power of minus 6, right, divided by delta Cs is 1.48. So, a ds equals to 12.1 into 10 power of minus 13 meter square per second. So, this is your salt diffusivity. So, you know, I hope you understand how we have proceeded and calculated the salt flux as well as water flux, salt diffusivity as well as water diffusivity inside the membrane, okay, by using the classic solution diffusion model. Okay. Please solve similar types of problem which are there in many of the books. Okay. So, we will see another problem which is actually based on a microfiltration this one data. So, the problem goes something like this: pure water with a flux of 30 meter cube per meter square hour enters through a polysulfone microporous membrane at a pressure drop of 1.5 bar at 25 degrees centigrade. The membrane is 70 micron thick and has an average porosity of 0.35 with an average pore size of 1 micron. Now, if the viscosity of water at 25 degrees centigrade is 0.9 centipoise, calculate the tortuosity factor of the pores, that is tau. The membrane resistance to flow, okay, what is that? Rm. then the water permeability, that is LP. Now, it is given that flow through the pores can be assumed to be laminar. Okay, it is a small problem. Let us see how we will do this. So, you have to use the classical Hagen-Poiseuille equation to solve this particular problem. So, the data provided is D diameter is 1 micron pore size, okay, pore diameter. So, your pressure drape delta P is given as 1.5 bar. Okay, so, 1.5 into 10 power of 5 Pascal. Okay. So, viscosity at 25 degrees centigrade, that is mu equals to 0.9 Cp equals to 9 into 10 power of minus 4 kg per meter second. So, then membrane thickness Lm is given as 70 micron. So, 70 into 10 power of minus 6 meters, again converting everything into meters and kilograms in that. So, that consistency will be there. Then porosity epsilon, okay, is also given 0.35, and water flux Jw is given 30 meter cube per meter square hour. So, you convert, we get 0.0083, okay. So, meter cube per meter square second. Okay. So, this is your water flux. So, this is all data is been given to us. Now, you use the Hagen-Poiseuille equation. Okay. So, use the Hagen-Poiseuille equation. Okay. So, what is that? Jw equals to epsilon d square divided by 32 mu into tau, then delta P by Lm, the thickness of the membrane. Okay. So, you substitute everything. So, 0.0083 equals to 0.35 into 10 power of minus 6. Okay. So, this is square divided by 32 into mu is your 9 into 10 power of minus 4 into tau, this is what we are going to calculate, okay, into 1.5 into 10 power of minus 5, that is your pressure, not minus 10 power of 5, that is the pressure drop divided by thickness, okay, that is 70 into 10 power of minus 6, the membrane thickness. So, from here you can calculate tau, okay. So, that is tortuosity equals to 3 to be calculated to be 3.14. Okay. So, the tortuosity factor for this particular problem is 3.14. Now, you have been asked to calculate the resistance to the flow. Okay. So, the resistance to the flow can be calculated from this equation. So, Jw equals to delta P divided by mu Rm, resistance to flow offered by the membrane Rm. So, from here we can write that Rm equals to delta P by mu into Jw. So, substitute. So, 1.5 10 power of 5 delta P divided by mu equals to 9 into 10 power of minus 4 into Jw equals to 0.0083. So, here Rm, the resistance to flow that is offered by membrane, has been calculated to be 2 into 10 power of 10 meter inverse. Okay. So, this is the resistance. So, now you have to calculate the water permeability. So, water permeability, which is known as LP. Okay. So, LP. So, that is also calculated equals to Jw by delta P. So, here Jw equals to LP into delta P. Okay. So, 0.0083 divided by 1.5 10 power of 5. So, here LP we get 5.53 into 10 power of minus 8. So, the units is meter cube per meter square second Pascal. This is 8. Okay. So, this is the water permeability. So, you see this is a very small problem actually. So, this is how we can calculate the water permeability, tortuosity factor as well as your resistance to the flow that is being offered by membrane using the classical Hagen-Poiseuille equation, right. So, I am not solving any complicated problems because that will take so much of time and you need so much of data from other handbooks and other things also. So, showing it here it is bit difficult and to show you that how to take from handbook and all it is bit difficult actually. So, when you actually face exam and all. So, my intention is just to show you that what type of problems, the simple problems that can be solved using the classical equations. We have seen the RO equations using the concentration polarization modulus equation, then we have calculated mass transfer coefficient, we have calculated salt flux, water flux. Then in the RO again using the classical solution diffusion model, we have calculated the salt diffusivity as well as the diffusivity of water inside the membrane. Now, for the microfiltration problem, we have used the Hagen-Poiseuille equation to calculate various parameters, whether it is your tau tortuosity factor, then we have calculated the membrane resistance and as well as the liquid permeability, water permeability. So, with this today I stop. So, please refer Professor B.K. Datta's book and Professor K. Nath's book for solving the numericals. There are so many numericals which are solved as well unsolved are given there, kindly refer to them, and in case you have any query you can write to me, I will definitely answer your queries. So, in the next lecture we will be solving some of the problems based on the ultrafiltration. So, thank you very much. If in case you have any query, please feel free to write to me at kmohanty@iitg.ac.in. Thank you.